Hello everyone. Let's continue our lecture in section 3.4. In the last lecture, we figured out how to find possible candidates for the roots of a polynomial. Specifically, when the leading coefficient was 1, we just looked at the factors of the constant term. But what happens when the leading coefficient is not 1? What we'd like to do is just generalize what we did in the last section. Okay, so let's take a look at just an example, and let's make some observations like we did before. So let's say that we have a polynomial, let's say p of x. And let's say the polynomial is, let's say it's 12x squared minus 7x minus 10. Now, you can go ahead and check this, but this polynomial will factor to a 3x plus 2 times a 4x minus 5. So, looking at its factored form, we can see that one of its roots will be, what will be one of its roots? It'll be a negative 2/3, and another one of its roots will be x equals, looks like 5/4. Okay. So how can I possibly figure out, just by looking at this polynomial, that its roots could possibly be negative 2/3 and 5/4? Well, let's make an observation. Observation. Okay, well, let's take a look at the numerator of my roots. Numerator of my roots. Look at the numerators, the 2 and the 5. Notice that 2 and 5, the 2 and the 5 are factors of the constant term negative 10. So 2 and 5 are factors of 10. Or factors of 10. Or how about negative 2 and 5 are negative 2 and 5 are factors of negative 10. Okay, what about the denominator? Denominator. The denominator of my roots, the 3 and the 4. The 3 and the 4, well, what are those factors of? Notice that they're factors of 12. Are factors of 12. The 2 and the 5, they're factors. The 2 and the 5 are factors. They're factors of the constant term. The constant term. And the 3 and the 5, these are factors. These are factors of the leading coefficient. And you can see why this works, just if we were to expand this. Notice if we were to FOIL this out, the 3x times the 4x would give you the 12x squared. So how would I possibly get this 3 and the 4? Well, they must be factors of the leading coefficient 12. How do we get the 2 and the negative 5? Well, when those multiply together, they give me out the negative 10. So the 2 and the 5 must be factors of the negative 10. So what I've just done here is I've just given you an example of what's called the rational roots theorem. So let's write this down. Let's generalize this idea. Let's write down let's write down the rational roots theorem. The rational roots theorem. Okay, the rational roots theorem. What it says if we have a polynomial, let's say p of x, and let's say, well, a general form of a polynomial is a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus plus a sub 1 x plus a naught. So if this polynomial has rational roots, or has a rational root. Let's say x. Let's say it's equal to, let's say, I know there's a p there. Let's say it's equal to, sure, how about we just put a p in a q? Put a p in a q. So P and Q are not, this isn't a function, these are just two numbers here. So what I mean by a rational root, the word rational, you should think of ratio or think of fractions. So if we have a polynomial that has some sort of fraction as a root, so this could be like 3/4, 5/7, or this could even be like 2 divided by 1, so 2 would be a root, or -3 divided by 1, -3 would be a root. So if a polynomial has a rational root of this form, then P, the numerator P, is a factor of A naught. Then the numerator is a factor of the constant term. And Q, the denominator of our possible rational root, is a factor of A sub n, which is the leading coefficient. This is what the rational roots theorem here says. Let's do an example of using it. Okay. Example. Let's say we have the polynomial. P of x, which is equal to, how about 2x cubed plus x squared minus 13x plus 6. Let's go ahead and try to write this polynomial in its factored form, find its roots, and let's draw a quick sketch of it. Notice, try as you might to try to factor this. You could try grouping, you'll find that it won't work. So we're going to try to use the rational roots theorem. We're going to try to come up with candidates for these zeros, or its roots. Okay, so this is what I like to do. So how do I look for the numerator of my roots? So here I'll write numerator, or just num for numerator. Okay, well the numerator comes from the factors of my constant term. So I'm going to look at the factors of 6. So I could get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay. Then I'm going to look at the denominator. What will be the possible? How do I find possible? What will the denominator possibly be? Well, the denominator for my roots will come from the factors of the leading coefficient. So from 2, so plus or minus 1, and plus or minus 2. So now what I want to do is I want to find all possible combinations of fractions where these are my numerators and these are my denominators. Now there's a certain way that I like to do this. Okay. So what I'm going to do is I'm going to start having a 1 as a denominator. So we're going to make our list. So we'll start with the 1 as our denominator. Okay, so I could possibly get a plus or minus 1 over 1. I could also possibly get a plus or minus 2 over 1. I could also get a plus or minus 3 over 1. Okay. So those are all the possibilities with having 1 in the denominator. Okay. Well, let's look at all our possibilities with 2 as our denominator. Okay. So what could I get? Oh, looks like I missed one. I'm sorry. We could have had plus or minus 6 divided by 1. So we also had plus or minus 6 over 1. Okay. Well, what else do we have? Well, we could also get plus or minus 1/2. We could also get plus or minus 2 over 2. We could also get plus or minus 3/2. Or we could also get plus or minus 6/2. So I've written down all possible combinations where these are the numerators of the fraction and these are the denominators of the fraction. Now when we're making our list, what we want to do is we want to get rid of all of our redundancies. Okay, so let's just write down a list without redundancies. Okay, so I have a plus or minus 1. We have a plus or minus 2. We have a plus or minus 3. We have a plus or minus 6. We also have the plus or minus 1/2. Okay, plus or minus 2 over 2, this is plus or minus 1. We've already recorded that, so we don't need to record this again. Okay, plus or minus 3/2. And plus or minus 6/2, well, 6/2 is equal to, what, 3? And I don't need to record that because I've already recorded it. So this is our list. So we have our recorded list of possible rational roots. So now what we're going to do is we're going to start checking them. Okay. So let's do it. This might be a good time for you to pause the video and try to factor this polynomial on your own. Go ahead and give that a shot. Okay. So let's set up our synthetic division bar. Let's check to see if 1 is a root. So we have 2, a 1, a negative 13, and a 6. Okay, we'll drop down the 2, and we're going to get a 2 here, 3, 3, we'll get out negative 10, we can almost see this is going to work. 1 times negative 10, going to be non-zero, 1 is not a root. Okay, let's check out negative 1. Okay, so bring down the 2, negative 2, add these together, I'll get a negative 1. Here I'll get a positive 1. Here I'm going to get a negative 12, and I already can see I'm not going to get a negative 6 here, so negative 1 also isn't a root. Bummer. Okay, let's check 2. Is 2 a root? Okay, drop down the 2. 2 times 2 is 4. 4 plus 1 is 5. Here we'll get out a 10. 10 plus negative 13, what we get, negative 3, and 2 times negative 3, negative 6, these add to give me 0. Bam! Bam! So we know that 2 is a root, so we know how this polynomial factors. This polynomial will have a factor of x minus 2 since 2 is a root, and this will factor to x minus 2 times a 2x squared plus a 5x minus a 3. Now if you want, you could continue to do synthetic division with this quadratic right here, but I know how to factor quadratics, so I'm just going to use our quadratic factoring skills here. You could use whatever method you want to factor this. My preferred method is the AC method. So let's kind of do a little aside. Let's go ahead and factor this. So for the AC method, I take the A and the C and I multiply them together. So 2 times negative 3. 2 times negative 3. Those multiply to give us a negative 6. I need factors of negative 6 that add to 5. So some sort of combination of 1 and 6. It needs to be a positive 5, so the 1 is a negative. These multiply to give me negative 6, and they add to give me 5. Okay, so this polynomial, let's break it up. This will be 2x squared. How about we write a minus x plus a 6x minus a 3. All I've done is I split up this middle term. We'll factor by grouping. Looks like I can factor an x out of here. So let's factor out an x. And we'll be left with, looks like what, a 2. We'll be left with a 2x. We'll be left with a 2x minus 1. Okay, what can I factor out of here? It looks like I can factor out a 3. So plus a 3, and I'll be left with, what, a 2x minus 1. Okay, so these two terms have a common factor of 2x minus 1. Let's factor that out front. So it's going to factor to a 2x minus 1 times that x plus 3. Beautiful. Okay, we fully factored this polynomial. So let's write it down. Okay, this polynomial factors to an x minus 2 times a, how we write it, is an x plus 3. It doesn't really matter what order you write these in. 2x minus 1. I don't know why, I just think this looks better, this order of multiplication. So this is the factored form of this polynomial. And now we can write down its roots. We know that x equals 2 is a root. It has a multiplicity of 1. We know that x equals negative 3 is a root, and that'll have a multiplicity of 1. And we also have that x equals, what, 1/2 will be a root, and it also has a multiplicity of 1. So let's go ahead and graph this. Let's graph it. Okay, its end behavior will be like a cubic. So here's our end behavior. Okay, it has a root at 2. Looks like it has a root at 2. Right here. Has a root at 2. It has a root at -3. Okay. It also has a root at 1/2. Okay, and let's look for its y-intercept. If I plug in 0, notice that p of 0, this will get zeroed out, that'll get zeroed out, that'll get zeroed out. P of 0 will just be 6. So I know the graph crosses here also. Okay, let's put the pieces together. Okay, so for -3 it has a multiplicity of 1, it has to cross through. I could have guessed that because it has to match up with my y-intercept and there's no extra roots here. Okay, now for 1/2 it has a multiplicity of 1, so it's going to cross through. And it's going to have to cross back through to match up. Notice it also has a multiplicity of 1. So here is a sketch of that polynomial. How fun is this? Okay, let's do one more example. Okay. Let's do the polynomial, or let's give a shot at factoring. How about a 4x cubed minus 13x squared minus a 37x plus a 10. So go ahead and pause the video, try to find the roots of this polynomial, and then try to graph it. Okay. So the first thing we're going to do here is we're going to find the possible candidates for the roots. We're going to list all the candidates for the roots given by the rational roots theorem. I think you might hear that language in some of the problems you might see. It says, find all the possible roots implied by the rational roots theorem, or something like that. Okay, so let's take a look at the possible numerator of my roots. The numerator of the roots will come from the 10, the constant term. And the denominator of my roots will come from the factors of the leading coefficient, the 4. So let's write all our combinations. We could get a plus or minus 1, a plus or minus 2, a plus or minus 5, and a plus or minus 10. Okay, we could also have plus or minus 1, a plus or minus 2, and a plus or minus 4. I'm going to go ahead and make our final list right here to have them recorded for us. Okay, so let's think about all the possible combinations where 1 is the denominator. So I'll think about these combinations. So I'll have a plus or minus 1 over plus or minus 1. So one possibility will be a plus or minus 1. I could also get a plus or minus 2 over 1, a plus or minus 5 over 1, and a plus or minus 10 over 1. So now let's find all the combinations where 2 is the denominator. So I'll get plus or minus 1/2. I haven't recorded that yet. Plus or minus 1/2. I'll get plus or minus 2 over 2. That's just plus or minus 1. We've already recorded it. We could also get plus or minus 5/2. And we could also get plus or minus 10/2. That's plus or minus 5. We already have that recorded. Okay, now let's check with the 4. Okay, so we could get plus or minus 1/4. We could also get plus or minus 2/4. It's the same as plus or minus 1/2. We have that recorded. We could also get plus or minus 5/4. Plus or minus 5/4. And we could also get, we haven't recorded that yet, and also plus or minus 10/4, but that's the same as 5/2. We already have that recorded, so we're finished. We have our list of possible rational roots, and I haven't recorded any redundancies. Okay, so let's start checking them. Okay, let's start with the 1. We'll check the 1 first. Let's record our coefficients. So 4, -13, -37, and 10. Okay. We'll bring down the 4. So 4, 1 times 4 is 4. 4 plus -13 will be what, a -9. 1 times -9, I'll get a -9 here. Okay, I can almost just pause here. When these add together, whatever the result I get, What is going to be negative, what, 46? When I multiply by 1, I'm not going to get negative 10. 1 is not a root. So let's check negative 1. Okay, so we'll drop down that 4. Negative 1 times 4, I'll get out a negative 4. I'll get now what, a negative 17. I'll get a positive 17 here. Okay, if I add those together, what am I going to get out? 20. Negative 1 times 20 is not negative 10, so negative 1 will not be a root. Okay, let's check 2. Let's check out 2. Is 2 a root? Okay, let's drop down the 4. 2 times 4 is 8. 8 plus negative 13, I think we'll get negative 5. So we'll get negative 5. Okay, 2 times negative 5, what we'll get out, what is negative 10? We'll get out negative 10. And when I add those together, what are we going to get? We're going to get out a negative 47. So it looks like 2 isn't going to work either. Bummer. Okay, we'll check out negative 2. We'll check out negative 2. Thank goodness for synthetic division. If we were doing polynomial long division, man, we'd be wasting so much paper, be hurting so many trees. Okay, negative 2. Negative 2 times 4, we get out a negative 8. Negative 8 and negative 13, I think that makes negative 21. Negative 2 and negative 21, what does that give me? That gives me a positive 42. Okay, negative 37 plus 42, I think I get out a positive 5. And negative 2 times 5, that's going to give me out a negative 10. Okay, when I add these together, I get out a 0. Sweet. So I know that negative 2 is a root of this polynomial. So how does it factor? It'll factor 2. If negative 2 is a root, then x plus 2 is a factor. And I'll be left with a 4x squared minus a 21x plus a 5. Okay. So now let's try to factor 4x squared minus 21 and x plus 5. Now, if you don't like my AC method of factoring, you could figure out what the zeros of this are. I mean, just by using the quadratic formula if you'd like, but I'm going to try to avoid that. So let's try to use the AC method. So 4 times 5, that'll give us 20. I want to find factors of 20 that add to negative 21. Well, let's see here. I think 20 and 1 have to work. 20 and 1. And I think they both have to be negative. They'll add to negative 21 and they'll multiply to give us 20. So we'll write this as, how about a 4x squared? Let's write this as minus 20x. And I'm going to write this as a plus a negative x and then plus a 5. So now we'll factor by grouping. Now whenever I do factoring by grouping, you have to make sure that this is a plus sign. You always need to, if there's a subtraction sign, you always need to add the opposite. Looks like I can factor out a 4x out of these parentheses. Let's factor out that 4 and an x. And we'll be left with, what, an x minus 5. And I can factor a negative out of this set of parentheses. So how about I just change that plus to, or how about I just do this? How about I do a plus? I'll factor out a negative 1. And so if I factor out a negative 1, this will leave me with x minus 5. So I have a common factor of x minus 5. We can factor that out front. So this will factor to a x minus 5 times a 4x minus 1. Beautiful. Okay. So we have this polynomial in its factored form. P of x will be equal to x plus 2 times a x minus 5 times a 4x minus 1. Okay. So let's check out its roots. It has a root of negative 2. It has a multiplicity of 1. It has a root of 5, and it also has a multiplicity of 1. And it also has a root of 1/4. 1/4 will be a root, and it also has a multiplicity of 1. So let's graph this. Let's graph this polynomial. Okay. Let's see. So it has a root of negative 2. So it has negative 2 as a root. Let's move the negative 2 over a little bit. So it'll have negative 2 as a root. It also has 5 as a root, and it also has, let's say, 1/4 as a root. Okay, let's check out its y-intercept. If I plug in 0, I'm going to get an output of 10. So I'll record 10 here. Its end behavior is like a cubic. Okay, since all these are multiplicities of 1, they'll just cross through. So the polynomial will look something like that. Awesome. Okay, so I'm going to go ahead and stop the video here. In the next video, I'm going to give you some tips on using synthetic division and using the rational roots theorem. Specifically, if we have something that's larger than a third degree. All the examples we've done so far, where it's always been third degree polynomials. And I'll also show you some tricks when we get down to a point where maybe that quadratic we possibly get at the end is unfactorable, and we'll show that we'll need to sometimes use the quadratic equation. Or the quadratic formula. Okay, I'll see you then. Take care.